before, they could be very complicated functions of x because it was linear first order. Okay? Now when you go to linear nth order, okay, things are not as simple, but the theories are all established. So what we're going to do today is discuss mostly the theory of nth order linear differential equations. Okay? This is it. And then we have to develop techniques to actually solve these. Okay? So let's look at the equation a little more carefully. Okay? We had this actually back probably the second week when we classified differential equations. Okay, and remember, I'm going to use this notation a lot. I remind you L on Y, because I don't want to write this whole mess on the left over and over again. It takes time to write it, okay? So whenever you see L on Y, it's basically a differential operator on the function y of x. In this differential equation, the independent variable is x, the dependent variable is y. And you notice on the left-hand side, what you really have is what? A linear combination of y, its first derivative, all the way up to the nth derivative, multiplied by functions of x. Okay? And the notation that the book uses is that the subscript on the coefficient matches the order of the derivative. Hence, a sub n of x, nth derivative y is back to x, right? a1 of x dy dx. And of course, here the derivative is 0, so it's a naught of xy equals g of x. Okay? So that's basically the problem that we want to look at. Okay? And recall, there's also another piece of vocabulary. When this g of x is identically 0, the equation is called homogeneous. And when you have g of x not identically 0, it's said to be inhomogeneous. And what we're going to find out is that we're going to start simple, solving the homogeneous equation, and we'll find that that's the key of solving the inhomogeneous one. Okay, well, let's keep looking at this inhomogeneous one and talk about the initial value problem. Again, this is more of a review because we did do this some months ago, initial value problem. The initial value problem is basically a coupled type of problem. It says, solve that differential equation subject to certain initial conditions. We know already that, or I told you that this thing is going to have n arbitrary constants in it. Go back to Newton's law again. N is equal to 2, right? Because you have the acceleration, the second of with respect to time. And you know from physics that in order to get a unique solution, you have to prescribe at time equal to 0 or any other reference time, the value of the position and the velocity. Okay? If you have a beam, okay, which unfortunately I'm not going to have time to go into this class, then we're going to have a fourth order equation, and then there are boundary conditions, again, 4 that you would specify. So in general, to get a unique solution, the number of initial conditions or boundary conditions that you prescribe matches the order of the equation. So we look at this equation and we see it's of order n. Okay, think now n greater than or equal to 2. Okay, so the initial value problem says solve that equation subject to the following initial conditions. Y of x0 is prescribed. I'll just call that number y0. Okay. The first derivative, y prime of x0 is prescribed. Let's just call that y1. All the way up to what? N minus first derivative. And I'll put that like that. Is equal to y sub n minus 1. Okay? So this is a number. So I'm telling you, solve this nth order differential equation, and hopefully get a unique solution. I'm going to give you the value, or someone's going to prescribe for you the value of y at a certain point, the value of its first derivative, all the way up to its n minus first derivative. Now, how many conditions are in here, right? Well, if you're specifying y up to its n minus first derivative, that's a total of n conditions, okay? And that's what we need. We need n initial conditions to solve that differential equation, to get a unique solution, that is, okay? Now, what makes this an initial value problem is you notice that all the prescribed data is at the same point. Maybe you have y at 0, y primed at 0, okay? There are other types of problems called boundary value problems, where maybe you have y at 0 and then the derivative at 1 at a different point, okay? And in mechanics, specifically things like, dynamics, it's typically, the position or maybe some other dependent variable at time 0, its derivative time 0, etc. Okay? So that's called the initial value problem. Okay. I'm going to state, but I'm not going to prove it. It's more of a graduate course, an existence uniqueness theorem for this, and it's going to be much more informative than the one we had for the nonlinear. You recall that when we had the nonlinear equation, we again stated without proof, we had dy dx as a function of x, y, and y prime, and that was nonlinear. And the theorem was kind of weak in the sense it didn't really tell you too much, right? I think it said something like if f and partial f, partial y were continuous in a certain region in the xy plane, okay, and there was a point x0, y0 on the curve, then a solution existed in some neighborhood at that point. And the problem was, what was the neighborhood. It didn't have to be the whole interval where it was continuous. That's called a local theorem. Over here, we're going to have a much more precise statement because the equation is linear. So it makes sense, right? The easier the equation, the more you can say about it. Okay. And again, I don't hold you responsible for this, in the sense of proving it but you should be able to, we're going to go through some problems and see why it's so important that you must have all these conditions. Existence, uniqueness. I spelled uniqueness correctly, okay? And basically, I'll say it in words and I'll write it down, okay? So what we want to know is, first of all, if I have this nth order differential equation, I give the n initial conditions, does a solution even exist? Maybe the solution doesn't exist, right? We've seen plenty of differential equations where the solution does not exist. And then the second question is, if it does exist, is the solution unique? That's important, right? Because if you have a well-posed physical problem, you can't have two people solve it, both get correct answers, and they're not the same. It has to be one and only one solution. So that's where the uniqueness comes in. And here's basically what has to happen. When you talk about differential equations, as I mentioned before, you always have to talk about a solution on an interval, okay? So let's consider some interval. Just call it AB. Okay, that's the interval that I'm considering. Maybe it's 0 to 1 or something like that, okay? What happens, in order to have a solution and it to be unique, all the coefficients in the differential equation, an of x, an minus 1 of x, all the way up to a naught have to be continuous in that interval, and g of x has to be continuous. That's one thing. And then another thing, which we'll see, it looks kind of strange at this point, this coefficient over here, the coefficient of the highest derivative, cannot vanish anywhere in the interval. That many times destroys uniqueness, and I'll give you an example of that. Okay? So 1, okay, is that all the coefficients, a sub n of x, a sub n minus 1 of x, dot, 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 down to a 0 of x, and the right-hand side, g of x, is supposed to be continuous in some interval. Let's say a less than or equal to x less than or equal to b. Okay? And that you can just probably see by inspection. You look at them typically, oh yeah, I can establish that they're continuous in a certain interval. Maybe it's restricted, maybe it's not from minus infinity to plus infinity, maybe it's on some interval between minus 1 and plus 1. But the coefficient is supposed to be continuous as an interval. Okay? And 2 is that leading coefficient, the coefficient of the highest derivative, is never 0 anywhere in the interval AB. Okay. Those two conditions are met, the solution exists and it's unique. Okay? Let me just give, let's just look at a couple of examples over here. Again, I'm not going to solve these, but sometimes just by knowing this theorem, you can actually say, oh, this happens actually sometimes. I shouldn't say many times you'll have a differential equation, and because of the physics of the problem, you can almost like guess what the solution is, okay? And then you can verify it, but then you have in the back of your mind, uh-oh, did I get every possible solution? And then if you have these conditions satisfied, you can say, yeah, even though I guessed the solution or I got it from some kind of trial and error type of thing, it's the right solution because of existence and uniqueness. Let's give example number 1 over here. This will be a very trivial one, okay? Suppose I have the equation 3, third derivative of y with respect to x, plus 5 times the second derivative of y with respect to x, minus dy dx, plus 7y is equal to 0. Okay, and let's give the following initial conditions. Y of 1 is equal to 0. The derivative at 1 is equal to 0. And finally, the second derivative at 1 is equal to 0. Okay, so that's a third order differential equation, right? Actually homogeneous, but certainly of that form, right, when n is equal to 3. And the coefficients are very simple in this case. They're constants, right? Everybody knows a constant is continuous everywhere, right? So the first condition is satisfied. All the coefficients, as well as the right-hand side, which in our case is 0, are continuous from x going to plus and minus infinity. Okay. And there's our initial data. And how many do we need? It's a third order equation, and I have 1, 2, 3 conditions. Okay. Just think, what's the most obvious solution to that equation? Someone can just guess.
Zero.
Zero, right? Y of x identically 0, right? Okay. It solves the equation, there's no question about that, right? And it solves the initial conditions. By this theorem, okay, because all the conditions are met, okay, the coefficients are continuous, and what's our an of x in this case? It's the coefficient of the highest derivative, which is 3. 3 never vanishes anywhere, okay? So therefore, you can just look at this and say, yeah, not a zero a solution, it's the only solution, because we have that theorem that we apply to. Okay, rather trivial. Okay, let's go to example number 2 then. Okay. Okay, here I'm going to have the second derivative of y with respect to x minus 4y equals 12x. And by the way, we're going to be solving all these. Now, right now I'm just going to give you the solution, but by the end of next week, we'll probably be able to solve all of these examples I'm giving you. Y double prime minus 4y equals 12x. Okay? I suppose the initial conditions are y of 0 is equal to 4, and the derivative at 0 is equal to 1. Okay. Okay. Okay, so let's talk about existence uniqueness, okay? I look at the coefficients of the differential equation in second order. I got 1, negative 4 on the left. Those guys are continuous everywhere. 12x is continuous everywhere, right? And therefore, and also the leading coefficient is 1 in this case, right? Because it's 1 y double prime. So that never vanishes. And we have two initial conditions. Solution has to be unique, okay? And I leave it to you just to verify that this is the solution. It's easy to verify. Again, I don't expect you to derive this at this point, but the solution is 3e to the 2x plus e to the minus 2x minus 3x. Okay? To verify, we've done this was probably the first week we did it, so I'm not going to do this on the board now. How do you verify that's a solution? Just plug it into the equation, differentiate, plug it in, you should get 12x, okay? And let's check at least that the initial conditions are satisfied, okay? So I'll do one derivative here, y prime, 6e to the 2x, right? Minus 2e to the minus 2x minus 3. Okay, what's y of 0? If I take my solution, plug in y equal to 0, I get 3 plus 1, which is 4, 4 minus 4, right? 4. So that checks. And what about the slope, or dy dx at 0 from the solution? Plug x equal to 0, I get 6 minus 2. Oh, 6 minus 2 minus 3, which is 1. So that checks out. Okay? And I leave it to you to just plug it in and show that it solves the equation. Okay. And again, that's the only solution. Okay? The most general solution, most general, the solution to this initial value problem. And notice basically there's no ambiguity over here with arbitrary constants. Everything is known. And that makes sense because we have a second order equation and two pieces of data were given, which has to be the case. Okay, now I'm going to give you one. And hopefully I'm going to ask somebody to tell me why this one is a little tricky. Example 3. Okay? The differential equation is the following. X squared y double prime minus 2xy prime plus 2y equals 6. And again, this equation, we're going to be able to solve this before the course is over. Okay, I won't have to give you the solution. X squared y double prime minus 2xy prime plus 2y equals 6. Y of 0 is 3. And y prime of 0 is 1. Okay, so let me say, so x squared y double prime minus 2xy prime plus 2y equals 6. Y of 0 is 3, and y prime of 0 is equal to 1. Solution, and we'll verify this. I claim the solution is y of x equals cx squared plus x plus 3, where c is an arbitrary constant. Okay, cx squared plus x plus 3, c is an arbitrary constant. Let's verify that this is the case. And then, of course, the question is, oh, what happened over here? I had a second order equation. I have two pieces of data. I should get a unique solution. Okay? Well, let me verify that indeed that's a solution to the equation. First, we'll plug into the differential equation, and then we'll check the initial data. Okay? Well, if y of x is equal to that, then by differentiating the purported solution, we get 2cx plus 1. Right? And the second derivative of y with respect to x, you just get 2c, right? Okay. So what's L operating on y in this case? Shorthand notation for the left-hand side, right? You got x squared times your second derivative, which is 2c, right? Minus 2x first derivative. And what's the first derivative? 2cx plus 1. Plus twice the solution, which would be 2cx squared plus 2x plus 6. Okay? Let me probably just do this in our head. Okay? What about the x squared? 2cx squared minus 4cx squared plus 2cx squared. Everybody see that? 2cx squared minus 4cx squared. There'll be minus 2cx squared plus 2cx squared. So all the x squared terms go out. Okay? What about the linear terms in x? Minus 2x times 1, it's a negative 2x and a plus 2x. So that goes out and that goes out. And indeed, you'll get 6. Okay? We never had to assume a value for c. C arbitrary, it just cancels out. It solves the equation. L on y is equal to 6. Okay? Let's check the initial data. Okay? What's my solution at x equal to 0? Let's see if it gives the right value. Y of 0 is 3. Is that right? Yeah, y of 0 is supposed to be 3. Let's take our solution differentiated and evaluate its derivative at x equal to 0. Here's our dy dx. At x equal to 0, it's 1. That's what I'm supposed to get. So that checks out. Okay, so someone tell me what happened over here. Okay? Right? Why isn't the theorem wrong, or is something basically not satisfied? Give you just a moment to think about that. Just go over all the conditions.
Condition 2?
Yes, condition 2. Yeah. What happens basically is that, let's go through condition number 1. Yeah, x squared is continuous everywhere, minus 2x is continuous, 2 is continuous, 6 is continuous.